Welcome back, all of you. I hope you have enjoyed and learned a lot through the previous lectures of vector differentiation. And now we will learn the vector integration. Vector integration is not as simple as you have learned the simple definite integrals. This is a special integral and called vector line integration. So before we try to understand what is the meaning of vector line integral and what it is, we will first actually we will proceed step by step. So as a first step, we will learn what is a unit vector, unit tangent vector to a curve. Then we will learn the vector line integral, and afterward in the next lecture we will understand what is the surface integral. So let us now start. To understand the concept of a line integral of a vector fields, first we should start understanding what is a unit tangent vector to a curve. Suppose you have a curve C, as you can see in the figure, and let P and Q be two neighboring points. If P, X, Y, Z be a point, then Q x plus delta x, y plus delta y, z plus delta z be a neighboring point of P on the curve. So if O be the origin of the frame of reference, then you can see that the position vectors of P and Q can be shown as OP and OQ. OP is represented by R means a vector R of XYZ, and then OQ is represented by R of x plus delta x, y plus delta y, z plus delta z, or you can say it is R plus delta R. So you know that the chord vector PQ can be calculated as OP minus OQ minus OP, and that is delta R. So you can see the chord vector delta R in the adjacent figure given here. So again, suppose that the length of the curve PQ, what is curve PQ? So PQ curve is this part, this from P to this Q, this is curve PQ. If the length of this curve be denoted by delta S, then what is the rate at which this radius vector is changing? So rate at which the radius vector is changing, that is called rate of change of R with respect to S, is denoted as delta R by delta S. So you already know this is the ratio. And now if in the limiting position, as Q tends to P, means we start moving this point Q slowly along P, then a condition will arrive when Q will almost collapse with P. In such condition, this chord PQ will become tangent to the curve at point P. In such condition, means in this limiting condition, if this ratio delta R by delta S exists, we say that dr by ds is, we define it dr by ds as limit delta tends to 0, and there this is a typing mistake, this should be read as 0. So delta s tends to 0, delta r by delta s. This is called the unit tangent vector at a point P of the curve. Now, if you have got the idea of unit tangent vector, we will use this fact to understand the line integral. Now we will try to understand the line integral. After learning the unit tangent vector, we are now in the position to understand this. So suppose we are taking the same figure as we did in understanding the unit tangent vector, and let there are 2 points, a point alpha and another point beta on the curve. Further, suppose we have a physical body, this is a physical body, and under some force F you move this body from alpha to beta. Now we are required to calculate the work done in moving this body from alpha to beta. From the simple Cartesian coordinate system, you know that at P, if the force applied is in this direction as I have shown, then this force will resolve in two components. A component parallel to the tangent means tangential component, let me say is Ft, and an other component in the direction perpendicular to Ft, and we say, let us say it Fo. So you know that this component FO will balance the frictional force between this body and the surface on which the body is sliding. This has nothing to do in moving this body. The only force component Ft will move this body. So Ft will move this body from alpha to beta. Now you know that if angle between F and Ft is theta at this point, then Ft can be simply calculated as Ft is equal to F dot unit tangent vector at the point P. And what is unit tangent vector? We have already seen that unit tangent vector is simply dr by ds, and r the conventions for r plus delta r and delta r. These are here, you can see in the figure. So this is the component of force that will under which this body will slide. So finally you can say this is the component of force, or this is the actual force for which you will calculate the work. So if we slide this body from P to Q, then the small work means the work done in sliding this body from P to Q is the work done in moving the body from P to Q is given by dW, and that is actually Ft ds. What is ds? Ds is the distance that you will cover while moving the body from P to Q. This is the point P and this is the point Q. So this distance is ds. So you will travel the distance s, means you will move the body by the distance s. So the work done is ft dot ds, and again ft you have already calculated. This is f dot dr by ds, and here another ds. So ds, this is the work done while moving the body from P to Q. Now what is the total work done? Total work done in moving the body from alpha to beta on the curve curve C. What is this? So this, if this work is denoted by W, then this is simply integral from alpha to beta dW, and we have already calculated dW. So this is alpha to beta f dot dr by ds, and under integral sign f dot dr by ds integrated with s, this will be simply alpha to beta f dot dr. So this is the concept of line integral. So work done, and finally I write this work done, this is equal to alpha to beta f dot dr. This is what we call line integral. Why line integral? Because the force is applying and the body is moving along this curve. So similarly, you can understand the concept for any field of vector is applying along a particular curve. A vector is working, simply you can say vector is working. It may be magnetic vector, it may be electric vector field, it may be gravitational vector field, any field. If vector is considered along this body, then integral of the vector along if this vector f is considered along this line, or you can say curve, then the line integral is simply calculated as the integral of f dot dr when alpha and beta the limits are taken according to the points on the curve. And sometimes when our vectors and the functions are represented in parametric form, you have already seen that when we took rt, the position vector of this form, cos t I plus sin t j plus t k, it shows a helical path. I have shown the graph in the previous lecture of vector differentiation. So this is the parameterized form of the vector. In this case, the function r will also be function of basically r of t, and in now the line integral alpha to beta f dot dr is simply written as alpha to beta f of r t dot d r t. So you already know that if r is function of t, then dr is written as dr by dt dt. So you means simply r dash t dt. You know that if rt is equal to sin t, then r dash dr is equal to cos t dt. So just using the chain rule concept, we will write the elementary form dr as r dash t dt, and this integral can be written as t naught to t1 f r t r dash t dt frt dot r dash t dt. This is because t is varying as a scalar quantity, and everything means every function f and r is depending on t. So now we will take some examples. So let us take our first example. If f is equal to x cube I plus yj plus zk be a force field, or simply you can say force. So this is a force field, means this is a force. Find the work done in moving a body from 1 to 3 to another point 3 5 7. So let us find how. We have seen what is the vector integral, so we will find the vector integral. And this is a nice thing that we have understand the vector integral, the line integral, by finding the work. So the work w will be this lower limit to upper limit, and let me say this alpha and this beta, so it makes us easier to write. So alpha to d beta f dot dr. Then you need to calculate what is f dot dr. So f is given here, and dr you already know, this is dxi plus dyj plus dzk. So f dot dr can be written as alpha to beta and x cube dx plus y dy plus z dz, and you can now integrate it. So the limits required will be taken from alpha and beta. So in the first integral only x is there, so limit is 1 to 3 x cube dx, plus in the second integral only y is there, so the limits will be 2 to 5 y dy. Similarly in the third integral only z is there, so limits will be 3 to 7 z dz, and now you can find it easily. x cube will integrate to x to the power 4 by 4. So this is x to the power 4 by 4 and limit is 1 to 3, plus this is y square by 2, limit is 2 to 5, plus z square by 2 and limit is 3 to 7. So you just now need to put these limits. So 3 to the power 4 minus 1 by 4 plus 5 square minus 2 square by 2 plus 7 square minus 3 square by 2. Just you need to compute these numerics and you will find the answer. Consider the second example. Second example, if the acceleration of a moving body is given by the vector A is equal to 18 cos 3t minus 8 sin 2t, this I component and this j component, plus 6t k component. Find the velocity and distance traveled at a time t if the initial velocity and initial distance is given. So if at t is equal to 0, velocity was 0 and initial distance travel was 0. So let us solve this. So you already know that a is acceleration and acceleration can be given as dv by dt. So dv by dt is 18 cos 3t I minus 8 sin 2t j plus 6t k. So to find velocity you just need to integrate this. So we just integral of this. So you will find 6 sin 3t I minus 4 plus 4 cos 2t j plus and this was 60k. This was 60k as written here, 60k. So you will get plus 3t square k plus a constant of integration. So you just need to apply the boundary condition, means v is equal to 0 at t is equal to 0. So at t is equal to 0, the velocity is 0 and first component sine component is 0 because sine 0 is 0. Second component, this is 4j because cos 0 is 1 and third component is also 0 plus c. So it comes out that c is equal to minus 4 times j. So just put the value of j. So value of c, the velocity is now 6 sine 3t I plus 4 cos 2t minus 4 j plus 3t square k. This is your velocity and I will not go to simplify. I will not going to simplify it further. You just need to find the distance traveled. So you know that ds by dt, this is v and you can say it r also. So dr by dt is v. So you just write the v as dr by dt and again integrate, again put the condition constant c and apply this s is equal to 0, or you can say it r is equal to 0. So you will find the value of distance travel. Now we will learn a very interesting theorem. You can also say it a property. If curl of a vector v is 0, means if a vector v is irrotational, rotational integral line integral alpha to beta v dot dr is path independent. Path independent means the integral does not depend on the path chosen, it does not depend on the line chosen, means it will depend only on the initial and final position. You can compare this to a conservative force. If a force is conservative and you have to move a body from a point A to B, then under conservative force field you can go from this way, you can go from this path, you can go from this path, you can choose another path will not affect the work done, only limiting only the points starting point A and B will contribute to the work done, means along all these paths you will do same work. This is the concept of conservative force, and same should be understood here. If V is rotational, it is equivalent to conservative, means the integral line integral will be path independent. So let us show this proof. We already know that V is rotational. This means curl of V is 0, and this implies there exists a scalar potential xyz, means a scalar function such that V is equal to grade of phi. And when we calculated grade phi in the vector differential operator, we can remind that and know that phi is calculated as integral V dot tr. So you can see the same integral is here. So when you are taking alpha to beta v dot dr, the line integral, it will just become alpha to beta phi. This will just integral alpha to beta will become actually phi. So this v dot dr plus a constant c, and this, so you will write this as phi alpha to beta, because phi has nothing to do with the integration process, it is independent. Simply v dot dr is phi, so this is independent of path. Just initial value alpha and final value beta will contribute to phi, so it is path independent. We will also take an example to show the concept we discussed just. So let v is given as xy square plus y cube I plus x square y plus 3xy square j. Then show that v is irrotational, and hence find evaluate the integral 1 to 2 3 4 v dot dr. So let us calculate this. So we first we need to find the curl of v to show that it is rotational. So curl of v can be calculated as I j k, then del by del x, del by del y, del by del z, and the components can be placed here. So xy square plus y cube and x square y plus 3xy square, and finally 0. So this is very simple, you can calculate and it will come to be 0. So this curl is 0, and this implies v is irrotational. So this also your homework to calculate that the curl is actually 0. Now because this is irrotational, we can find phi as this v dot dr, and you can also find phi otherwise, but we discussed the special method to find phi when v is rotational. So what this plus c, so what was that method? Just write phi v dot dr x y square plus y cube dx plus x square y plus 3xy square dy plus c. And we had discussed in the previous lecture of vector differentiation that when curl v is 0, we integrate it with a special technique, means integrate the first integral taking y as constant, so we will get 1 by 2 x square y square plus y cube x. Now we will integrate the second one with respect to y, but the only those terms will be integrated which are free from y. So no term is free from y, so we just write c. Now we have phi, and with the help of this phi you can compute this 1 to 3, sorry 1 to 2 and 3 to 4 v dot dr. This is simply 1 to x square y square plus y cube x, and limit 1 to 2, 3 to 4. So either put limits of x first or put the limit of y first, and you will get 254. So this is the method of obtaining line integral if a vector is irrotational. So finally, I hope you have understood what is the concept of line integral and what are their applications. And in next lecture, we will continue vector integration, but we will discuss the surface integral in the context of vectorial surface. So keep waiting for the next lecture, and till then, keep on your study for previous lectures and this line integral.